Welcome back to this series on topology. In today's video, we'll be starting to look at compactness, which can be seen as a generalization of being bounded and closed in Euclidean space. As always, you can find a playlist containing all the videos in this series by clicking on the info thing that should appear right now. Also, if you enjoy these videos, please consider giving them a like so that other people can find them more easily. Now, before getting started, I'd like to say that the definition of compactness might seem a bit strange at first if you're not used to this sort of thing, but in fact it turns out to be one of the most important definitions in topology. So if at first you don't quite understand what the definition is trying to do, just bear with it, and I'll promise that in a few videos' time it'll become apparent why compactness is so important. The definition of compactness is phrased in terms of open covers of a topological space. So before being able to say what it means for a space to be compact, we need to define what an open cover of a topological space is. An open cover of some topological space X is nothing but a collection of open subsets of that space whose union is the entire space. So if this here schematically is our topological space X, then an open cover is nothing but a selection of open subsets of X. So these orange sets here would be some open subsets of X, and the only requirement on this collection being an open cover, aside from the fact that its elements are open, is that they need to cover the entire space so that the union of all of these subsets is X again. So usually we'll denote the elements of an open cover by the same letter but not curly, so the elements here would be U alpha, where alpha lives in some index set A, and well, the condition on this being an open cover is that on the one hand these U alpha are open, and also that the union of these U alpha over all the alpha in A is the entire space X. Okay, so an open cover is pretty simple. It's basically what it sounds like. And the reason we'll be interested in open covers in general is because open covers provide you a way of decomposing your space into open sets, and if you have objects that are defined locally, so on some open sets of your space, then open cover can allow you to define objects on separate parts of your space and then somehow glue them together. For instance, we might have a family of functions f alpha going from U alpha to some other topological space Y, and let's suppose that each of these functions f alpha is continuous. So for each element in our open cover U alpha, we might have such a function f alpha going from U alpha to Y. And now if these functions agree on the places where these open sets U alpha overlap, then in fact we can assemble them into a global continuous function going from X to Y. And well, the reason for this is that these U alphas cover the entire space, so at each point in X we know where to send it, and because the f alpha agree on overlaps, we won't have any conflicts during this assignment. And finally, well, because continuity is a local property, so it suffices to be continuous on neighborhoods around each point, it means that the result will again be continuous. So if you want, you can check all of these claims in more detail, but this example is just to illustrate how one generally uses open covers of a topological space in order to assemble local data into some global object. The second thing we'll need in order to define compactness is the idea of a subcover. So a subcover of a open cover U is a subcollection of elements of U that still covers the entire space. So again, schematically, if we have our space X here, and we're given some open cover of the space, so again, we have certain open subsets which cover the entire space, well, then some of these subsets might be redundant. For example, I might have a subset here which basically covers the same area that some other subset covers. So instead, I could just remove that subset and I would still have an open cover. And this cover that results from removing certain open sets from our open cover will be called a subcover. So in this case, the elements I'm surrounding in purple here, these would form a subcover. So it's all the elements except for this orange element here. Okay, so we've defined what an open cover is, and we have this idea of a subcover being some sub-collection of some open cover that still covers the space. And now a natural question that arises is, well, if you have some open cover, like how many elements can you remove while still retaining its covering property? Or in other words, what is the smallest subcover that's contained in a given open cover? Now, compactness is related to this question. Namely, a space is called compact if every open cover of that space has a finite subcover. This means that compactness answers the question I asked before about like what is the smallest subcover we can find in a given open cover. It answers this question by saying that regardless how large your open cover is, you can always reduce it to a finite number of open sets that still cover the space. Illustrating this definition pictorially is a bit difficult because I can only ever draw finite covers of a space, but let me just say again what compactness means. So suppose we have some space X and we have some collection U, which consists of elements U alpha, where alpha is some index in an index set A, and each of these U alpha here is open. And moreover, we're assuming that it's a cover, so the union of all these U alphas has to equal the entire space X. So this is what it means to be an open cover of X. And now if X is compact, so if X is compact, then in fact, finitely many of these sets U alpha suffice to cover X. So this means that there exists some finite collection, which I'll call U alpha sub k, where k runs from 1 to n, such that the union over all these U alpha k, where k runs from 1 to n, is still X. So here I'm choosing finitely many elements of this collection U alpha, indexed by k going from 1 to n, and moreover, these elements still have to cover X, so the union of all these U alpha k is X. And this is what it means for X to be compact. If regardless of what open cover I choose, so here this index set could be infinite, I can always choose a finite subcollection that still covers the space. Okay, so I said before at the beginning of the video that compactness can be viewed as a generalization of being bounded and closed in Euclidean space, and this is something we'll prove towards the end of our look at compactness in a future video, namely the Heine-Borel theorem, which states exactly that a subset of Euclidean space is compact if and only if it's bounded and closed. So that's one way to think about compactness. But another way is to just use this definition and think of it as a sort of finiteness property. From this perspective, compactness allows you to reduce some infinite object, namely an arbitrary open cover here, to some finite object, which is, in this case, a finite subcover. And in general, working with finite objects is easier than working with infinite objects. For instance, a finite collection of numbers always has a maximum, but an infinite collection might not. And similarly, if you have a finite collection of open sets, then you can say more about what's going on there than if you have an infinite collection. Finally, before giving some examples, I'll also define what it means for a subset of some topological space to be compact, namely a subset A of a topological space X is called compact if it is compact in the subspace topology. This is exactly analogous to what we did with connectedness. So we defined what it means for a space to be connected in its entirety, and then we said that a subset is connected if it's connected in the subspace topology. All right, so to illustrate what compactness looks like, let's give some examples. So the first one is very basic. It's saying that every finite space is compact. Let's think about why this is the case. Well, the reason for this is that finite spaces have a finite number of subsets. So if the cardinality of X is equal to n, then the power set of X has 2 to the n elements. This means that you can have at most 2 to the n open subsets, because that's the total number of distinct subsets you have in such a finite space. In particular, any open cover will also have a finite number of elements to begin with, because you only have finitely many open sets, so such a finite space is compact by default. The next example is similar. It says that every space with a trivial topology is compact. So recall that the trivial topology means the topology that only consists of the empty set and the entire space. And so again, here we have finitely many open sets to start with, so any open cover of such a space will have to be finite to start with. So maybe we could sum up these examples A and B by saying that if your space has a finite topology, so it only has finitely many open sets, then it's a compact space. Note also that in the case of the trivial topology, we have exactly 2 open covers, namely the one that consists only of the subset X, and also the one that consists of the entire topology, namely the one with the empty set and X. The last example I'll give is a bit more involved than the previous ones, but still pretty basic. It says that a subset of a discrete space is compact if and only if that subset is finite. Okay, so let's prove first the right to left direction. So suppose we have a finite subset of a discrete space. Well, by the example A, we know that every finite space is compact. So in particular, a finite subset of a discrete space is a finite space if we consider it with the subspace topology, and so it's compact by example A. So this shows this right to left direction. The second thing we have to show is that if a subset of the discrete space is compact, then it has to be finite. And the way we're going to do this is by showing that every infinite subset of a discrete space cannot be compact. For this, we suppose that A is some subset of a discrete space X, where the cardinality of A is infinite. And now remember that a discrete space is one in which every subset is open. In particular, singletons are open in the discrete topology. And this fact will allow us to construct an open cover that cannot have a finite subcover. We'll define U to be the following open cover, namely the open cover consisting of all the singletons, small a, where A lies in this subset capital A. This is indeed an open cover because each of these singleton subsets is open in the discrete topology, and moreover, because we've chosen singletons for each point small a in the set capital A, the union of all these singleton sets small a is the entire set A, and hence it's a cover. Now, if our subset A were compact, then it needs to be possible to find a finite subcover of this open cover U, but this cannot be the case because if we get rid of any element of this open cover U, we'll be leaving out some point in our subset A. In other words, there's no proper subcollection of U that still covers our set A. In particular, there's no finite subcover of U because we've assumed A to be infinite, and so if we had a finite subcover, this would have to be a proper subcover of this open cover U. So in summary, we've shown that whenever we have an infinite subset of a discrete space, we can construct this type of open cover which does not have any finite subcover. And therefore, this subset cannot be compact because we've exhibited an open cover that does not have a finite subcover. Thus, in some sense, discrete spaces have too many open sets to be compact, because whenever you have some infinite subset of a discrete space, you can form this open cover here consisting of these singletons. And because you've chosen singletons, it means that you can't remove any of the elements of that open cover, and hence you can't form a finite subcover. All right, so these 3 examples are pretty basic, and they're the ones that you can easily show that they're compact. We'll see one more example later in this video, and then in future videos we'll also see that closed and bounded subsets of Euclidean space are compact. And this is basically the main example you should have in mind when thinking about compactness. You should think of bounded and closed subsets in Euclidean space, but proving that they are compact will be a whole thing and is too involved to do as one of these initial examples. Next, I'd like to discuss the compactness of subsets of a space in a bit more detail. So we said by definition that such a subset of a space is compact if it is compact in the subspace topology. This works fine as a definition, but it's maybe not always the most direct way you could check that a subset is compact, because you kind of have to switch between different topologies if you're trying to check that a subset of some given space is compact. And this lemma is basically saying that there's an alternative way to check that a subset is compact, namely the following. It says that a subset A of a space X is compact if and only if the following holds, namely that every collection of open sets U alpha of the space X that satisfies that A is contained in the union of these U alphas. So we can think of this condition here as saying that these U alpha cover A in the sense that, well, A is contained in their union. So if every such collection of open subsets has a finite subcollection, U alpha k, that still contains the set A. All right, so the statement might look a bit complicated, but it's basically saying the same thing as the definition of compactness, except that we don't have equality holding here, but inclusion. So looking at it through this lens, it says that a subset A of X is compact if every open cover of A in X, so that would be a collection U alpha of open subsets of X that covers A in the sense that their union contains A. If every such open cover of A in X has a finite subcover, so that would be a finite subcollection U alpha k of that original open cover whose union still contains A. Now the advantage of this lemma is that here you're working with open subsets U alpha of the space X rather than open subsets of the subspace topology of A. And the reason it's true is essentially because if you have such a collection U alpha of subsets of X that cover A in this sense, and you intersect them with A, then you get an open cover of A. And well, this condition here with the finite subcollection is then just saying that whenever you have such an open cover of A, you get a finite subcover. Let's prove this in a bit more detail, and then maybe also the statement will become clearer. So the first direction we'll prove is left to right, which assumes that we have a subset which is compact in the sense of our original definition, and then we have to show this second condition. So we suppose that A is compact in the sense of our original definition, which was as a subspace. Okay, and now we need to show that for every collection of open subsets of X which cover A, we have a finite subcollection that still cover A. So for this we let U alpha be a collection of open subsets of X that cover A in the sense that their union contains A. Okay, and now we're going to move to subspaces, so we're going to consider a new collection, namely the U alphas intersected with A. Now the claim is that this is an open cover of A viewed as a subspace. The reason for this is that, well, each of these sets is open in the subspace topology. Basically, by definition, the open sets in the subspace topology are intersections of open sets of the larger space with the subset you're considering. And now the second thing we need to show in order to show that this is an open cover is that it covers A. So we need to show that the union over these U alpha intersect A, so each of these sets over all alpha, that this is equal to A. Now by the distributive property of unions over intersections, this is the same thing as the union over all alpha of U alpha, and this entire thing intersected with the set A. All right, but now we know by assumption that this big union here contains A by assumption. And therefore, if we intersect it with A, what we get back is A itself. Okay, so this argument in orange here, well, shows that this collection here is an open cover of A, where we view A as a topological space in its own right using the subspace topology. Okay, and now, well, we assume that A is compact, which means that this open cover here will have a finite subcover. So we have some finite subcover, which I'll denote U alpha k intersect A, where k goes from 1 to n. So this is a finite subcover. And now we need to somehow extract out these U alpha k's here and show that they satisfy this last condition in the lemma. So we consider the collection of these U alpha k, which we obtained by getting the finite subcover of this original intersected open cover of the space A. So this collection here is exactly of the form we need, and the only thing we need to check is that the union over all these U alpha k contains A. And well, this follows from the fact that this thing here is a subcover, so it still covers A. To show this more formally, we know that A is equal to the union over k from 1 to n of these sets U alpha k intersect A, because this collection here is a subcover of this original open cover, which means that it still has to cover A. Now again, using the distributive property for unions and intersections, this is the same thing as the union from k from 1 to n over all these U alpha k, and this entire thing intersected with A. And now we have the situation where we have some set that we intersect with A, and the result we get back is A. And well, this implies that this union here has to contain A. Why is this the case? Well, if there were some point in A which is not contained in the union, then that point would also not show up in the intersection, and this would contradict the fact that this intersection is equal to A. Therefore, every point in A also has to be contained in this union, and that's exactly what we wanted to show this part of the lemma. All right, so the notation here is a bit of a mess because we have all of these collections and then we change them around, but the basic idea of this direction is that, well, if you have one of these collections U alpha of open subsets of X that cover A in this sense, then you can intersect each of these elements in the collection with A, and what you get is an open cover of A, so you can use the compactness assumption we had to produce a finite subcover, and then if you again extract the finitely many U alpha k you get by doing this, this thing will satisfy the conclusions of the lemma in that direction. Now for the other direction, we assume this condition which I'm calling star, which is that every collection of open subsets of X whose union contains A has a finite subcollection U alpha k whose union still contains A. And what we want to show is that this implies that A is compact as a subspace. Okay, so we're supposing star. And now we need to show that A is compact as a subspace. In other words, every open cover of A in the subspace topology needs to have a finite subcover. So we let U alpha be such an open cover. Now, because each of these U alphas is open in the subspace topology, by definition it means that U alpha is some intersection of an open set of X with A. So U alpha is equal to the intersection of some set V alpha with A, where V alpha is an open set of X. Now, since we know that A is equal to the union of these U alpha, But we also know that the U alphas are actually of the form V alpha intersect A. And again, using the distributive property, this is the same as the union of the V alphas, and the entire thing here intersected with A. This implies, using the same argument I sketched before, that we must have that the union of these V alphas contains A. Again, here we're intersecting some set with A, and we're getting back A, so this set here has to contain every point in the set A. All right, so we started with an open cover of A with these U alphas. Then we wrote these U alphas as intersections of V alphas, where V alpha are open subsets of X with our original space A. And now we've shown that the fact that these U alpha cover A means that this union of the V alphas has to contain the space A. And this is exactly what the assumption of star is, namely that we have some collection now that's called V alpha of open subsets of X whose union contains A. So now by our assumption, we know that there exists some finite subcollection V alpha K, where K runs from 1 to n, such that the union of these V alpha K still contains A. Now we need to transport this thing back to our subspace A, and the way we do that is by intersecting with A. So we let U alpha K be the intersection of V alpha K with A. So that's basically just taking a subcollection of the U alpha, namely those U alpha which are obtained from the intersection of some V alpha K with A. Okay, and now the last thing we need to do is we need to show that these U alpha K are actually a finite subcover of this original open cover U alpha. The first thing we need to check is to check that these U alpha K actually are a subcollection of this original collection. But this is the case because each of these U alpha K is some V alpha K intersected with A, and the V alpha Ks are a subcollection of the V alphas, so the U alpha Ks are also going to be a subcollection of the U alphas. And the second thing we need to check is that this is actually a subcover, which means that these U alpha K still cover A. Okay, so I'm claiming that this collection here is a subcover. And the reason for this is that if we look at the union over K from 1 to n of these U alpha K, then by definition this is the union over V alpha K intersect A, which using the distributive property is the union over the V alpha K intersect A, and by assumption the union of the V alpha K contain A, which means that if we intersect the union of the V alpha K with A, we just get back A. And this is exactly what we needed to show, because this shows that the union of the U alpha K is equal to A. So this thing here is indeed a subcover. In summary, we've taken an arbitrary open cover of A, and we've shown that it has a subcover which, well, is indexed by a finite index set, and this is exactly what we need in order to show that A is compact in the subspace topology. Okay, so I hope this whole proof wasn't too confusing. Basically, we have these two related notions, either being compact in the sense that you're compact as a subspace, and then also there's this sort of refined version of the compactness definition where you take subsets of the larger space that somehow cover your subspace, and these two things turn out to be the same because you can go in between open covers in either sense fairly easily. We can now use the previous lemma to give an example that's a bit more interesting. So for this we assume that X is some topological space, and we suppose we have some sequence xi of points in X that converges to a limit y which also lies in X. Now the claim is that the subset A, consisting of all the points of the sequence, including this limit, that this subset here is compact. For instance, a special case of this example would be the following, we take the real line and we look at the sequence 1 over n, where n goes from 1 to infinity. So this would be the points 1, 1/2, 1/3, and so on. And while this sequence converges to 0, then our subset A would consist of the points 1 over n, where n is a natural number greater or equal to 1, and also unioned with the point 0. Then the claim of this example is that this subset here would be compact in the real line. But of course, the example is much more general because it applies to all convergent sequences in some topological space. All right, so let's see why this is true. Now, one way to prove this would be to use the direct definition of what it means for a subset to be compact. So we would check compactness in the subspace topology. But now instead we can use the previous lemma and use the alternative characterization of compact subsets. So for this we let U alpha be a collection of open subsets of X that satisfy that the union over all of these U alphas contains our set A. And now we have to show that there is a finite subcollection of this collection U alpha that still contains the set A. And the way we're going to do this is we're going to use the definition of convergence. So in particular, well, there must exist some U alpha 0 that contains the limit y, because, well, y is an element of A, and we've assumed that A is contained in the union of the U alphas, so this means there has to be some U alpha 0 that contains y. Okay, but now we've found an open subset of our space X which contains the limit, so this implies that, well, all but finitely many of the points in our sequence xi are actually contained in U alpha 0. So there exists some natural number, let's call it capital N in N, such that, well, for all n larger or equal to n, we have xn lies in U alpha 0. And again, this is just the definition of what it means for this sequence xi to converge to y. It means that whenever you choose an open neighborhood of y, so an open set containing y, there is some natural number capital N such that for all natural numbers larger than this capital N, the sequence lies within this open set. Okay, but now we're sort of done because, well, we've chosen this one open set in this cover here, and we've shown that all but finitely many points of the sequence lie within U alpha 0. So this means we only have a finite number of other sequence points we need to deal with, and so it shouldn't be too difficult to come up with a finite number of these sets U alpha that contain these finitely many points. Now for each m that's strictly less than capital N, we let U alpha m be an element of this collection U alpha that contains xm. So here I'm just saying that for every m that's strictly less than this threshold capital N, we just take some open set of the collection U alpha that contains xm. And the reason there is such a U alpha m that contains such an arbitrary element of the sequence is that the union of all these U alpha contains A, so every element xm of the sequence, well, this lies in A, so it must lie in some element of this collection. We now consider the collection U alpha k, where k runs from 0 to m, and this satisfies that the union going from k from 0 to m over all these sets U alpha k contains A. Why is this the case? Well, if you take any element of A, it's either of the form xi or y. So we know that y is contained in this u alpha 0, which is an element of this collection here. Now, in the case where the element of A is going to be of the form xi, we have two cases. Either I is strictly less than n, and in this case we've included an element u alpha m into this collection that contains this point xm. So that case is good. And if in the other case the I is greater or equal to n, then by the fact that the sequence converges, it means that this xi will be contained in u alpha 0. And this is also an element of the collection. Therefore, regardless which point we choose in A, we have some element u alpha k of this original collection that contains that point. And we've managed to reduce the number of these elements to a finite number by using the fact that the sequence converges. Okay, and now, well, we've taken such an arbitrary collection of sets that cover our set A, and we've managed to reduce it to a finite subcollection that still covers A, and using the lemma from before, this shows that A is compact. So I noticed here that perhaps there's a bit of an issue with the indexing. So in order to make this work the way I've set it up, we don't want to have m be 0 in this indexing here because we already have a u alpha 0. So here m has to be greater or equal to 1, which means that the indexing convention for the sequence should have been that I starts at 1 and goes to infinity. And so here in A, we shouldn't have xi where I lies in the natural numbers n including 0, but rather in n greater or equal to 1. Alright, so far we've seen that in certain basic cases we can directly use the definition of compactness, or this lemma we proved, in order to show that certain spaces are compact. However, similar to the case of connectedness, it's kind of difficult to prove directly from the definition that things are compact because you have to show that every open cover, regardless how it's constructed, can be reduced to a finite subcover. Therefore, in order to deal with compactness, it'll be very important to have results that certain operations on compact spaces again produce compact spaces. Now, if you recall from the discussion of connectedness, we had this important theorem that stated that the images of connected space under a continuous function is again connected. And this allowed us to basically prove connectedness for only very few spaces and then sort of transport this along continuous functions to more complicated spaces. We're going to do a similar thing for compactness, and in fact the analogous theorem is also true for compact spaces, namely that if we have topological spaces x and y, and we have a continuous function f going from x to y, then if the space x is compact, then so is its image f of x. So this is exactly analogous to connectedness, where we saw that the images of connected spaces under continuous functions are again connected. We also have that the images of compact spaces under continuous functions are compact. And again, a consequence of this theorem will be that if you can prove that a certain space is compact, then you can transport compactness to some other more complicated space by mapping it through a continuous function. Writing down the proof of this theorem will again not be so nice because we have to work with these open covers and index sets and so on, but the basic idea is pretty simple. We start with an arbitrary open cover of the image f of x, and well, we need to be able to show that there is some finite subcover of this open cover. And the way we're going to do this is we're going to pull back the open cover of the image f of x along the continuous function, and what we get is some open cover of our space x, which we know to be compact. Therefore, this pulled back open cover on x has a finite subcover, which we can then push forward along the function f to get a finite subcover of our original open cover of the image. All right, let's start writing this down more precisely. So we start with considering some collection u alpha of open subsets of y which cover the image f of x. So the U alpha are open subsets of Y that satisfy that the union over these U alpha contains f of x. So here I'm again going to use the lemma we proved previously in order to show that this subset f of x is compact. In order to do this, we need to show that there is some finite subcollection of these U alpha that still cover the set f of x. And again, as I said before, we're going to pull back these U alpha to the space X along F. So we consider the collection F inverse of U alpha, again indexed by the same index set. So these here are the pre-images of the U alphas under F. And well, we know that these pre-images are going to be open because F is continuous and the U alphas are open. And in order to show that these are actually an open cover of the space X, we need to show that their union is equal to X. One way to see that these pre-images of the U alpha cover X is as follows. So we know that, well, pre-images are compatible with unions. So the pre-image of the union of all these U alphas is the same as the union of the pre-images. So this is something you can check for yourself if you haven't seen this already. Moreover, pre-images are also compatible with containment, which means that because the union of these U alphas contains the image f of x, this implies that the pre-image of these union of the U alphas will contain the pre-image of f of x. Okay, but now if you think about what this here on the right is saying, it's saying that you're considering the pre-image of the image of the entire domain set. So that's all the points in X which map to the image f of x. But of course, every point in X maps to the image f of x by definition, so this is equal to the entire set X. Okay, so on the one hand, we've shown that the union of these pre-images of the U alpha is equal to the pre-image of the union of these U alphas. But on the other hand, the pre-image of this union here is also equal to X. So therefore, the union of the pre-images of the U alpha is equal to X. So this new collection consisting of the pre-images of the U alphas is an open cover of X. All right, now because X is compact, we know that there exists some finite subcover of this original open cover consisting of the F inverse of the U alpha k. So we're picking finitely many elements, and these will have the form F inverse of some U alpha k, where k runs from 1 to n. Okay, and this is a subcover. So in particular, it still covers the entire space X. And now the final thing we'll do is we'll push forward this subcover on X back to Y and show that it's going to be a subcover of our original cover U alpha. So what we do is we consider these U alpha k, where k's are the same indices, so these alpha k are the same sub-collection of the original alphas that we got here from this subcover. So clearly this is a sub-collection of this original collection U alpha because we've just selected certain alpha k. Now the thing we need to show in order to apply the lemma from before is that the union of these U alpha k is still containing the image f of x. One way to see this is by contradiction. So we suppose that there is some point y in the image f of x such that, well, y is not contained in the union of these U alpha k. This in turn implies that the preimage of y cannot be contained in the preimage of this union. The reason for this is that if this preimage of y were contained in the preimage of the union, then if we map forward with f, this would imply that y would be contained in the union, which it is not by assumption. So perhaps here a little picture would be nice. So consider this set here to be the union of these u alpha k, and then we also have our point y. And now we're considering the preimages of these points under f. So there'll be some preimage set of y. And then there'll be some preimage set of this set here. And now by definition, these preimages are all the points that map to the respective set. So these here in blue are all the points that map to y, and this here in pink are all the points that map to the orange larger set. And well, now if this preimage of y, this blue set, were contained in the pink set, then by definition this would mean that it is mapped into this larger orange set here, which in our specific case would be the union of the u alpha k, and this would then in turn mean that y is contained in this union, which it is not. Therefore, this preimage here can't be contained in the preimage of the u alpha k. In fact, it is disjoint from this preimage because, well, this entire blue set is mapped to y, which is not an element of this set here. Okay, but now on the other hand, because again, preimages are compatible with unions, this means that this set here, the preimage of this union, this is the same set as the union of the preimages of the u alpha k. But by assumption, these preimages of the u alpha k are a subcover, so this means that their union is equal to x. And here's where we obtain a contradiction, because, well, we were assuming that there's some point y in the image which is not contained in the union of these u alpha k, and this implies then that the preimage of y is not contained in x. Therefore, we conclude that there can't be any point y in the image that is not contained in this union. So therefore, the union of these u alpha k's must contain the image f of x, and this is exactly what we need in order to apply the lemma, and this shows that the image f of x is compact. All right, so as you can see, writing everything down is a bit of a mess, but again, the idea is very simple. We assume that x is compact. We want to show that its image f of x is compact, so we take some collection of subsets which are open and cover f of x, we pull them back along f, and because f is continuous, these pulled back sets will still be open in x, and moreover, they will cover x because they covered the image f of x. And because x is compact, we can now reduce this collection to a finite collection of sets which still cover x, and then we can push these sets again forward along f and get a finite collection of our original collection that covers this image set. Okay, with that, I'm done with what I want to say for this first part on compactness. So we've seen the definition of compactness, we've seen some very basic examples. Now in this final theorem, which is maybe the most important property of compact spaces, we've seen that the image of compact spaces under continuous functions is again compact. In the next two videos, we'll be continuing our look at compactness. So next time, we'll be showing some more basic properties about compact spaces. Then in the final video on compactness, we'll show the Heine-Borel theorem, which states that the compact subsets of Euclidean space are precisely those subsets which are closed and bounded. And we'll also show a version of the extremal value theorem for compact spaces, which says that whenever you have a compact space and a continuous function going to the real numbers, then that function attains its minimum and maximum.